you need the mic?
Yeah, thank you.
There we go.
Good morning, everyone. My name is Yunqi Zhang from the nanomechanical lab of the NTU, as well as the Zhiliang Clinical. Here, my title is the study of the hydrogen-induced plug-in in X65 pipeline steel by using the X65 framework. The main part of this work is not only the material itself, it's what the X65 framework can do. The most important of this framework is it can simulate the ductile reduction of the material and the ductile or brittle transition. In this study, we will first time to see the CGM+ framework to predict the fracture toughness and the resistance curve of a real-time named X65 pipeline steel. Here's my outline. First is a recap of the X65 framework. Second is the basic introduction of the single spaceman experimental results. Then I will show my results of the 3D single spaceman. And next is the preliminary results of the 3D pipelines model. And finally will be the summary and the perspective. Okay. The CGM+ framework can be presented as this figure. As we started with the right side with the deep blue curve one. This is basically the material response as the pure air condition. You can see the curve is have one significant of active fracture. The MVC region of the fracture surface is basically dominated by the wall nucleation, both growth and both coalescence. And with the increase of the hydrogen content, this model combines the hydrogen diffusion and the trapping. So they will stay with the void-based mechanism, but it will have hydrogen expressed ductile fracture. And the dimple size and the void size will become smaller than the spaceman in the air. And still under this condition, it will combine the mechanism with the carbon mechanism. Hydrogen enhances the local velocity, and the helium mechanism. Hydrogen enhances the string-induced vacancy. Consider these two mechanisms. This model can predict the hydrogen suppressed ductile fracture, and still with the equation of the hydrogen content. The mechanism switch to the tidal. The hydrogen enhanced the decompression mechanism domain. In this area is basically the hydrogen assisted with the brittle fracture. So, and the actual material can endure with the maximal volume of the hydrogen. It will have a response like a pure brittle fracture. So this model is basically can predict both the hydrogen expressed ductile fracture mechanism and the hydrogen assisted brittle fracture mechanism. It can predict from the ductile to brittle transition of the material. I think that is the most important of the capacity of this framework. And I'm basically introduce this experimental results. This experimental is tested by our colleague, and this is the geometry of this baseline. You can see the CDOD, the positive over in this place and at the positive, and the CMOD at the different of the major location. The reason why we chose the center baseline because of the center baseline is mostly closer to the real pipeline part of the industry So we can just change the quark length to make this thin spaceman suit the real industry practice. Oh. So this is very true the thin spaceman because the thin spaceman can represent the industry need. Here are the test results. Here is the CMOD and the load flow of the spaceman with the increase of the hydrogen. With the increase of the gas hydrogen, you can see the black loads of the spaceman. Similarly, by monitoring the maximum, the CQD value at the maximum load, you can see clearly of the dark loads of the spaceman, especially when the hydrogen is firstly added to the material. It has a very significant reduce of the toughness of the spaceman. Here is my simulation model. The left figure is about geometries and the mesh and the element mesh and of the spaceman. And the right figure is basically the boundary condition of the spaceman. Two directions of symmetries and displacement loading at the constant speed. And the hydrogen boundary condition. Because of the spaceman has been immersed with the hydrogen content for a long time, so we can get the uniform hydrogen distribution of the spaceman. So the initial chemical potential is applied here to make the simulated hydrogen. Here is my simulation results. The left figure is the experimental, and the right figure is my simulation result. You can see at the same part, with the increase of the loading, the particle keep bluntly, and it keep a propagation given the direction. And this figure is the results of the simulation results and the experimental results. All the solid line and the experimental results and the dashed line is the simulation results. You can see the results. You can see the CGM+Framework and predict the CMOD and the load flow of the experimental results. And the right figure is also the results between the experimental and the simulation. The blue one is the simulation result, and the red one is the experimental results. It shows the same frequency with the increase of the hydrogen, the magnificent of the dark loads of the spaceman. Here is a similar experimental result from another paper because of the measurement of the CPOD value is very difficult for the experiments. And the next one is the simulation. Consider of the without the hydrogen and with the hydrogen is the condition. You can see at this figure at the catalytic potential. You can see the factor loops and the partial resilience curve is going down under the hydrogen condition. This one I give a very big of the hydrogen content. You can see it's very clear of the partial resilience. It's loose due to the hydrogen content. And now here are some simulation results of the structure integrity of the pipeline section. It's the pipeline section. It's the pipeline, and we have a pyramid part. at the interior of the pipeline section. You can see the part table is at here. Here is the basis distribution of the specimen. And similar, the hydrogen content distribution have a similar tendency. And with the increase of the loading, you can see the fracture process of this specimen at the beginning. The fracture going along this direction is the radial fracture at the beginning, and then it finish the radial fracture. It will keep fracture under the hook direction until the whole section go to failure. Here is the simulation results. Under the condition without pressure, just with the hydrogen, you can see how hydrogen suppress the ductile of the specimen. A very significant of ductile loss. And with the condition of the gas hydrogen, with the pressure, it can increase the load, but also lead to the ductile loss of the specimen. And the worst condition with the hydrogen gas, both the pressure and the hydrogen, the biggest of the ductile loss of the specimen. So I think it can predict the worst situation of the industry. And with the increase of the hydrogen content, you can see the CMOD transit of the specimen. It starts from the health domain mechanism. The ductile is keep losing, but very significant losing at this area, and the transit getting more flat if we just keep increase the hydrogen content, because in this area is basically the head domain. Here is the conclusions, and there are some take-home message. The first one is the hydrogen CGM+Framework can predict the fluctuations of 3D specimen and the hydrogen condition. The second is the hydrogen CGM+Framework can also be used to predict the effect of the hydrogen on the structure unit of the last structure, such as text. The final one is the hydrogen. It's the CGM+Framework can potentially enable the transferability from small scale net tests at the 3D center specimen to the structure unity of the larger scale structure, like the pipe section and the service condition. Thank you. And any questions?